We've been looking at heating the metal to allow the molten pool to penetrate and fuse. All that heat also has an effect on the base metal itself. Metal is made up of groups of atoms bonding together to form grains. When metal is heated past a certain temperature and cooled quickly, smaller grains are formed, making the metal harder. Cooling the metal slowly allows more atoms to bond, forming larger grains, which makes the metal softer. In welding, the metal adjacent to the weld bead becomes hot enough to change the structure of the grains. Because only a relatively small area is heated, the metal cools quickly, forming smaller grains and becoming harder right alongside the weld. Welding also causes the pieces of metal in the joint to draw. Heated metal expands, so during the weld, the molten filler metal is deposited in its maximum expanded state. As it cools, it contracts. When the metal is free to move, it will draw in the direction of the weld. If the pieces being welded are trapped, the molten weld metal still contracts, leaving some residual stress in the metal. There isn't any way to stop this. The metal is going to move. Whenever possible, weld on both sides to reduce the draw, and on pipe or square tubing, use a sequence of welds to help control the draw. Extreme differences in temperature do have a greater effect on the metal. If it's freezing cold, use a torch to heat the metal up a little. Condensation will appear, and just warm it up until the moisture dries. Also, if you are welding on harder, higher carbon steel, which does not handle expansion and contraction very well, a preheat may be necessary to prevent the weld from cracking as it cools. As always, there are a lot of variables, the type of steel and the stress that will be put on the finished product. In most cases, projects are designed so that the stress put on the weld joint does not come anywhere close to the maximum strength of either the metal or the weld. Try to complete the weld once you start it and avoid building up more weld than necessary. When you're finished, let the metal cool slowly. If the metal does break next to the weld, you may need to take a closer look at the thickness of the metal being used and the overall design. Okay, let's take a look at putting two pieces of metal together. The first steps with any type of weld joint are metal preparation and joint fit up. If you're working with new metal, most of the rods can handle the mill scale, which is a dark layer on the surface. Use a grinder to clean any metal that's rusted or painted. Impurities on the surface can cause porosity, lack of fusion, or even interfere with the arc. When you're cutting metal, keep the edges straight and square. If you use a torch, chip or grind off any slag left from the cutting process. During fit-up, use good tacks to hold the pieces together, and if you're leaving a gap, keep it uniform. Irregular gaps in the joint not only take longer to weld, they make it way more difficult than it should be. You can avoid a lot of problems by cleaning the metal and taking your time on fit-up. While there are many variations of weld joints, there is generally considered to be 4 types: butt joints, lap joints, T-joints, and corner joints. On a butt joint, the weld should penetrate deep, with the amount of weld deposit at least equal to the thickness of the metal. For maximum strength, 100% penetration welds are used to completely fuse the edges. On a lap joint, the weld is called a fillet, with the legs coming up and out a distance equal to the thickness of the metal and the weld slightly crowned. A fillet is also used on T-joints, where the edge of one piece is joined to the surface of another. Welding on both sides reduces the amount of weld necessary and overall produces a stronger joint. Corners are joining the edges at an angle, with metal preparation or fit-up allowing for sufficient penetration and weld deposit.